Libby Hopfauf. I'm the Program Manager and Audiovisual Archivist for Moving Image Preservation of Puget Sound, or MIPoPS, and I'm also the Audiovisual Archivist for Seattle Municipal Archives.
Hi, my name is Andrew Weaver, and I work for the University of Washington Libraries as the Media Preservation Librarian.
And I'm Dave Rice. I'm the co-chair of the AMIA Open Source Committee.
Welcome to another DVRescue update. Today we're going to explore various aspects of debugging and troubleshooting encountered in this project. But first, for those of you who aren't familiar with it, here's a brief overview of what DVRescue is. Funded by a research and development grant from the National Endowment for the Humanities, DVRescue is a set of tools designed for preserving archival videotape in DV formats. Over the past 2 years, this project has developed procedures and tools that support migrating data from DV tapes into digital files suitable for long-term preservation. This has helped fill an urgent need for DV tape transfer tools that can rescue content from at-risk digital videotape formats. Components include transfer analysis, file packaging and merging, as well as assistance and guidance.
For this presentation, we're going to share behind-the-scenes development stories of the DVRescue project in order to focus on the concept of debugging. The term debugging is most often applied to computer programming, but here we're using the term more broadly to define any workflow or any actions that are taken to identify, diagnose, and resolve problems in a workflow, wherever that workflow is carried out by a computer, a machine, or a person. And we find that even though you can learn in the classroom, through skill sharing, through expertise, through putting all your education to use in an actual archival environment, when we're working with information that is broken or malformed, that has deteriorated, that doesn't follow the specifications exactly, that errors will happen. Our workflows will become broken. The work of debugging, of trying to figure out like what went wrong, what is broken, how to fix it, is often where we have the greatest learning opportunity, where we can really test what we've been told, what we've learned, and see if it's true. In debugging, we have to design experiments, create hypotheses, perform tests through tedious trial and error to refine and find where the error is, how to fix it, or how to work around it. In general, we develop workflows and tools based around common routines of our work in the areas of preservation. The expected parts of a workflow can be challenged when we work with material that is deteriorated, unstandardized, or broken. As obsolescence and deterioration is blended throughout a project, so much of our work turns into handling the corner cases and planning for the exceptions rather than just handling everything as if it was normal. We all know the moment when we realize that what worked perfectly over here fails over here. It worked on my computer and it doesn't work on yours. And then there's that struggle to perceive what the difference is. When we do this work, the meticulous planning and the investigations, and then we crash into these corner cases, we move into a debugging mode. In a learning environment, often the lesson focuses on what to do and how it's supposed to work, but how do we proceed when we followed all the instructions perfectly and it doesn't? That work to diagnose and resolve is often where our greatest learning experiences and most of effective research is going to occur. Those moments of facing surprise challenges and exceptions can be frustrating and they can embarrass us in live demos, but these moments put the experimental method and learning opportunities right before us. The DVRescue project is filled with many of these examples. So in this presentation, we're going to share a few stories of bumping into unexpected results and debugging our way through it.
Before you even start using the tools, you need to ensure that your transfer station is set up properly and ready to roll. This part of the presentation will focus on equipment and hardware troubleshooting and possible solutions for Mac, Windows, and Linux setups for DV transfer stations. There's a lot less equipment involved in capturing DV videotape versus other analog formats. For DV transfer, all you need is a deck with a compatible power cord, a FireWire cable that corresponds with your deck's DV output, a computer, and possibly a dongle or two. This is an example of a Mac setup. Theoretically, the setup should be plug and play, but that's not always the case. As with all troubleshooting, you need to make sure you only change one variable at a time. This may sound tedious, but it is the best way to ensure that you accurately identify the problem and will understand exactly how to fix it in the future. We recommend actively documenting all steps taken during troubleshooting so that you have a record which may come in handy in the future. This can be a passive process of screen recording or active, taking notes or voice memos to yourself throughout the process. Of course, it helps a great deal to have a guinea pig, and that's where our communications manager, Paul Seipel, comes in. More on that later in the program. Even if your deck is connected properly and all the cables are working, your computer might not be able to communicate with it due to improper settings. Before using a deck, we recommend reading through the operation manual to ensure that you have set it up correctly. At MIPoPS, we always earmark all of the pages that list the errors provided by the deck for quick access. For example, with the Sony DSR 1500A, in the device menu, the input needs to be set to iLink on the face of the deck, as well as in the remote IF menu. VAR, or variable, should be set to playback, or PB. Output should be set to DV video. These settings will vary in title and requirements based on the deck. We have collected the operation and in some cases maintenance manuals for all DV decks currently at MIPoPS. They are available as part of our deck guide on the DVRescue website. We encourage contributions of additional images, manuals, and relevant personal experiences for these and any other DV decks. Please note, in order to use deck control, you will need to have your deck in remote versus local mode. However, this shouldn't affect the ability for the computer to read the device. But in this section, we are mainly focusing on hardware and equipment, everything leading up to actually using any of the DVRescue tools. Transfer will eventually be integrated into the DVRescue GUI, but for now, we're using ViewRecord, which the DVRescue project was able to successfully integrate DV capture into. Connect your deck to the computer using the required cable and adapters if needed. Make sure that the cables are inserted all the way into the Mac computer port and that all adapters used are securely connected. Turn on the deck. Check your connection by opening the terminal and running ViewRecord E. When you open ViewRecord in Edit Settings mode, click on the DV tab. There should be a list of devices to select from, depending on how many decks or external components you have connected to the computer you are using via FireWire connection. But as you can see, nothing is showing up. Why is that? First off, ensure all of your cables are not bent at a hard angle or straining to reach either the deck or the computer and are properly supported. All three of these factors can cause cable failure. Next, to rule out that it's not an issue with ViewRecord or DVRescue, check what devices your computer is recognizing. You can do this a few different ways, but the easiest is with QuickTime. Launch QuickTime, and from the File menu, select New Movie Recording. A new window will open, and if you click the arrow next to the Record button, input and outputs should be listed, and your deck should show up under Camera and Microphone. If it is not there, then there is a problem with one of your other connections, which I will address shortly. If it does, then you'll want to try a series of reboots to get ViewRecord to recognize the device. Try turning the deck off and restarting your computer. For the most part, one reboot does the trick, but every once in a while, especially with older computers, it may take a few attempts and a lot of patience before the deck will finally pop up in ViewRecord. I'm not over-exaggerating when I say once all I did was restart my Mac Mini 5 times, and on the 5th attempt, the computer recognized my deck as a device and I was good to go. If the device doesn't show up in ViewRecord after the 3rd reboot, try waiting longer between when the computer has booted back up and when you turn the deck back on. Still not there? Time to test your connections. Any one of these components could have failed, and you'll need to test them one by one. A lot of the troubleshooting steps we recommend assume that you have additional cords, cables, decks, or other FireWire devices to test out the connections. We do advise purchasing multiple cables even if you only have one deck for this very reason. Cables can fail and it's hard to narrow down the cause if you don't have anything to test it. In this order, execute each of the following steps to determine the root cause. Whenever you order an adapter, you should always order 2 so that there is a backup in case one fails. Another thing to pay attention to when ordering an adapter for USB-C ports, make sure that the dongle is compatible with Thunderbolt 2 and that it is capable of data transfers, not just display. Unfortunately, Apple adapters, the most expensive ones, seem to have a longer lifespan and are more trustworthy than other brands at this time. We are currently working on a choose-your-own-adventure style visual step-by-step guide for troubleshooting these steps. Once complete, it will be available with our other documentation resources on the DVRescue website. One of the many exciting facets of this project is the cross-platform capabilities. A Linux Windows setup provides an inexpensive option for a DV transfer station. The equipment needed includes a refurbished computer and a FireWire card. Not all of these setups are created equal. While some are plug and play, others require more work. Here are some issues and possible solutions that we encountered while setting up the second PC Linux transfer station. The Windows Linux setup includes, in our cases, a refurbished PC. We purchased a Dell for both because we found the first one for a good deal, and after its success, we didn't want to change too many variables right away. This does not mean that it's the best option or our official recommendation. It's just what we have tried. This is accompanied with a DV card which enables the user to plug a DV deck directly into the PC tower. Our first attempt by Andrew Weaver was essentially seamless. The FireWire card was installed, computer partitioned, software installed, and everything was good to go. Now, while this first setup was basically plug and play, our second one did not go as smoothly. We ordered another set of equipment and had MIPoPS communication manager Paul serve as our guinea pig in order to ensure that we documented all necessary instructions for creating a Windows Linux setup and to assess the intuitiveness of the process to people less familiar with PCs. The FireWire card was easily installed. However, as soon as Paul started the partitioning process, things began to go wrong. One of the many frustrating things about troubleshooting is that sometimes you have to wait a good 30 to 45 or more minutes to know if what you tried worked before you can adjust a variable and try again. This was the case with this setup attempt. In order to document the process, Paul, Andrew Weaver, and myself all participated in a Zoom call in order to record everything for note-taking purposes and to document all of the proper steps. What was intended to be a 45-minute endeavor turned out to be a 4.5-hour-long call with lots of head scratching, researching, and troubleshooting. First off, the attempted partition experience was much different than the instructions provided. Prompts did not come as expected, and partitioning continued to freeze. Boot permissions for USB devices was disabled by default. This must be fixed in order to boot the Ubuntu installer for Linux from a USB stick. Checking the permissions is not listed in any directions for partitioning this computer. It took quite a bit of digging before we discovered that this was a necessary step within the boot menu. You also need to ensure that the installer you downloaded is correct. Although he followed the steps Andrew sent him, Paul's installer was not the same, but luckily Andrew could drive over and deliver a USB stick with the proper installer. We also discovered that once Ubuntu was properly installed, the computer will need an Ethernet connection to be able to download the drivers needed to use the Bluetooth dongle that comes with the kit. A Wi-Fi connection or hotspot will not work. We are working on compiling all of these troubleshooting steps into a document in order to provide support to users who want to attempt this setup.
Another aspect of the DVRescue project with a high ratio of debugging is around a process called DV Packager. Packaging here means taking a .dv file and encapsulating it into a container format like QuickTime or Matroska, and then adding in audio, timecode, recording metadata, and chapters along with that original DV as is into a container format. To do this, DV Packager will first evaluate the DV file coming from tape and determine where certain events are occurring, such as changes in the technical audiovisual properties. This first category actually includes events like switching your DV camera from 16:9 to 4:3 aspect ratio mid-recording, or changing from 2 audio channels to 4, or even from PAL to NTSC. Most recordings do not contain these types of transitions, so when they do occur in DV, it makes sense to split that DV file at those transition points and package each part separately. Other events notable for DV Packager are things like recording start markers, timecode jumps, and jumps in the recording time. So DV Packager can split DV into separate packaged files based on any of these events. For each event, we note the byte offset of the associated DV frame, as well as the frame number, the presentation timestamp, and the timecode. So the debugging story here is about how we go about cutting one file into pieces. This example here shows a DVRescue XML of a DV file that contains 2 recording start markers. So we can take this DV file and package it into 3 separate QuickTime files, 1 per recording start marker. So we can make 3 files of these 3 time ranges, but when our DV Packager process asks FFmpeg to do this, we would sometimes get results that were 1 frame off. We have a frame of the middle section, for instance, at the end of the beginning section. When we started debugging, we found that we needed to calculate frame timestamps with greater precision. NTSC, for instance, is 30,000 divided by 1001 frames per second, which is about 29.97 frames per second, but it is actually this never-ending number. So we cleaned up the math and we standardized to start using microsecond precision, which is to the millionth of a second. This helps fix some of the issues, but we still found examples where DV Packager was not cutting exactly at the right place, and a single frame that should be at the beginning of one section was at the end of the prior section. So with more debugging, we next realized that we had a discrepancy between how timestamps were rounded to a microsecond between FFmpeg and DVRescue. one of these tools was always rounding to the nearest microsecond, and one of them was always rounding down. So we matched the methods between the systems, and then we fixed the issue. But then this same problem turned up on a new file we found. When debugging then, we found even more of our assumptions were challenged. We had presumed that every DV frame has the exact same duration. An NTSC frame is 1001/3000th of a second, and a PAL frame is 1/25th of a second. The file causing the issue now was already in a QuickTime container, and we found that that QuickTime container gave some frames different durations. This QuickTime file contained an edit list as a means to try to cover up dropped frames by extending the duration of the prior frame to fill in the gap. So then we set DVPackager to ask FFmpeg to ignore QuickTime edit lists and to export frames at an exact clock interval. So yay, the problem is then fixed, but then of course we find another file that exhibits the same problem that we've already solved many times before. So now we find that in this sample, it's DV also in a QuickTime file, and that QuickTime file added a small delay to the initial timestamps so that all the frames are slightly offset in time. And now at this point, the process of determining exactly where to cut DV files into pieces is working, at least until we find another exception to the rule that challenges our presumptions. So in summing this up, some of these solutions were quick to find. Some of these required tedious debugging and experimentation to find the right solution. And other times, finding the right solution required knowing when to put the problem down, take a walk, and think about it later. There's one corner of the DVRescue project that has driven our development work into a spirit of debugging from the beginning. This involves a function of the software called DVmerge. DV tapes will play imperfectly, and the playback deck will conceal the errors and note the presence and location of concealment within the digital results. Parts of the audio may be silenced with an error code, or parts of the video that are errored will be concealed by copying over a part of a prior frame. When we play a DV tape once, we may see and hear those artifacts of concealment, whether it's because the tape is damaged or the deck is dirty. However, when we play that same tape again, we may see and hear those artifacts of concealment in different places. The dust bunnies can roll over, contamination on a playback head may be moved or brushed away. In our 2020 AMIA presentation, we demonstrated an early version of this DVmerge function, which could take multiple DV files generated by reading the same tape multiple times and then evaluating them to find the location and occurrence of video and audio concealment. Then we would merge the best parts of multiple attempted reads of the same tape into one consolidated output. We were essentially taking the best of multiple reads and cherry picking from them to create a better output than would be possible from a single continuous DV tape reading. So this function is developed and it works well, but it fails very well too. There's a lot about it that works wonderfully, with frames put back together, creating seamless, near-perfect transfers by essentially adding a double take to the process of reading, allowing us to misread something once and try to read it a second time, knowing that we can merge and assemble everything back together as the playback deck is verifying if the read is correct or not for each pass. But when we examine the failures, though, they come from a small part of how I described this function. And that is about determining how we know what is a corresponding frame between all the copies. How we take these frames and we align them between all the transfers. The first piece of data that we can try to use to create this type of alignment is timecode. Even though many parts of the frame might be damaged or concealed, the timecode value itself in a DV frame is designed to be one of the most resilient pieces of data in the frame. Each DV frame contains 20 80-byte blocks called subcode, which carries the timecode and carries several redundant copies of timecode in each one. This image is showing a single frame and all the various expressions of timecode that just appear in one frame. This redundancy is part of the design of DV to make sure that the timecode value can be read even if the tape is in shuttle mode or being fast forward or rewound. So we can find the first timecode value and then align the frames and merge the pieces together. Still, sometimes the time codes don't line up because of the way damaged DV frames work. When the audio block is read from the tape and broken or damaged, the deck will conceal the damaged audio by sending silent error codes. When a video block is damaged or misread from the tape, the deck will send a copy of that same piece of the frame from a prior frame. But when subcode blocks are damaged, the place where the timecode lives, we just get the damaged subcode block. Because of this, sometimes in the damaged frame, the timecode value is written into multiple places, but some of them might be wrong. Some of them might be based on corrupted data. So we have to create a strategy where we can't simply presume the DV frame is healthy and written properly according to the spec, but we have to use the reality of how a DV frame works when we're designing the software. So rather than just taking the first timecode value we find and using that, we have to read all the timecode values and take the one that is the most commonly occurring one in the frame. So that way, in case the first value is broken, we can most likely find the more correct copies elsewhere in the frame and use those. This fixes some of our unexpected results, but others remain. So in debugging, we next find that we have to acknowledge that timecode itself is not a value that we can count on to be a unique value to uniquely identify a frame in a DV recording. For instance, this image is from DVRescue's Analysis tab, showing a home recording that I made on MiniDV. Each one of these orange markers on the timeline represent a timecode jump or reset where the timecode is set back to 0. If we're trying to identify a frame uniquely, then information such as like the timecode equals 1 minute, 12 seconds, and 8 frames is not a unique reference. It could be referring to several different DV frames. So if we're trying to cross-reference and align different parts of the tape together, timecode isn't sufficient to do this in all cases. So in trying to resolve this, we went back to the subcode section of DV frames. This animation here shows the first subcode block of each DV frame with the encoded timecode values seen incrementing in green. So as we look for more data here to uniquely identify the DV frames, another value stands out. From frame to frame, there's another pattern of incrementing values here shown in blue. We didn't know what this was or if it was possibly helpful, so we went back to the DV specification to figure out what it was. SMPTE 314M defines DV, so we look it up and eventually we find a reference to this data which simply calls these values arbitrary bits. Within this specification, these arbitrary bits are not further defined, but the name implies that there's no reason or meaning to this data at all. Even though it looks helpful and it looks like an identifier, SMPTE calls these arbitrary bits, but we don't have to buy that. Fortunately, DV also has a specification written by the International Electrotechnical Commission, so we bought access to this document and dug in. In this document, the same values we found were not called arbitrary, but the IEC calls this data value the absolute track number. This was an exciting discovery as it seems that this value is very specifically for DV recordings made by hardware, where the absolute track number is a 23-bit value that increments based on each helical pass of the head across the tape. Even as the timecode may be reset in the tape, the absolute track number more consistently continues to increment. Essentially, this number acts like a measurement that says how far into the tape you are. We found a few edge cases where an absolute track number could be reset in the middle of a tape, but this number is far more continuous in the reality of DV than timecode has been. Still, trying to identify a DV frame according to the absolute track number leads to even more problems and more need to debug. This value is written less redundantly than timecode, there's less copies of it, and fragile damaged tape will corrupt this value or exclude it. So we've been working on developing a series of tests to figure out what absolute track number is for a certain frame. These reports show an example of trying to recover every absolute track number from a series of frames in order to create a method to determine which ones are likely correct and which ones are likely incorrect. You can see missing values, some values that are off because of bit flips, but by looking at the trends of each occurrence within each frame, we can generally develop some formula to refine out what is most likely to be an accurate representation of an absolute track number for a given frame. So presently, we're experimenting with using a combination of absolute track number and timecode And hopefully, with continued debugging, all this will resolve into an improved function for merging multiple DV tape recordings together, which could help us build tools to improve the overall accuracy of DV preservation workflow.
Hi, I'm Andrew, and I'm going to talk about an example of debugging that we went through that kind of built upon itself into multiple layers of debugging. Also, hopefully this will show a little bit of our process that we went through while developing DVRescue, and will also help to illustrate how some of the DVRescue features can be used for debugging and analysis of DV files in your own workflows. So what ended up to be the initial catalyst for this round of debugging was the need to stress test the various capture frameworks to underlay the DV capture function of DVRescue on its 3 supported platforms. This involved making repeat transfers of the same tapes to allow us to see in a semi-controlled manner how the frameworks would perform. This also, as you will see, ended up with us having 8 separate captures from the same edited program that serendipitously proved to be quite useful both for debugging DVRescue as well as to highlight the kind of provenance and quality control options that the DVRescue approach to tape migration opens up. More on that later, but first about our initial debugging need. Since a lot of the initial development work on DVRescue was done on the Mac side, one of our steps to start translating across platforms was to make sure that our strategy for capture on Linux and Windows was viable, with our strategy being to integrate the FFmpeg capture devices available for those respective platforms. These being the DShow device for working with Microsoft's DirectShow framework, and the IEC 61883 device for tapping into DV streams on Linux. We approached this process with a little bit of trepidation, as initial stress tests on the Mac side, which compared the AVFCTL tool developed by DVRescue for capture with the AV Foundation device in FFmpeg for capture on Macs, had shown that the FFmpeg device was resulting in significantly more dropouts than AVFCTL. Our methodology for debugging the consistency of the transfers was to compare the resulting sizes of the output files, as well as check how many times the DVRescue XML tool noted non-consecutive timecodes. Fortunately for us, it turns out that we had nothing really to worry about, and the FFmpeg devices on Windows and Linux performed very admirably. Starting out with the Windows side, you'll see that we, for the most part, had very consistent file sizes, and apart from one initial transfer that had an abnormal amount of timecode discrepancies, everything came out pretty much the same. Even better turned out to be the capture process on Linux, where we, as you can see, end up with not only identical file sizes, but the same 0 amount of timecode discrepancies across all 4 captures of the same tape. So all in all, this part of the process resulted in a happy output for debugging, where we realized that there weren't actually any bugs that were occurring on Windows or Linux that need to be dealt with. This process then led us to the next aspect of DVRescue that we wanted to test: the ability to merge multiple captures of the same tape to end up with as perfect a representation of the original tape material as possible. Since the framework stress test resulted in us having 8 copies of the same tape, it was perfect fodder to run through the merge process. For the record, in an actual workflow, 8 captures would be way overkill for getting enough data to maximize merge results, but we figured since we had them, we might as well use them all. During this stage, we were approaching the DVRescue process with the following 2 hypotheses: that looking at whether error concealment data was coming from odd or even diff blocks within frames would allow a user to differentiate between a head clog or other types of damage like a scratch, as well as that these kinds of head clog errors would be highly repairable by the DVRescue merge process, as the chance of a head clog happening in exactly the same way, in exactly the same location in separate transfers, should be relatively low. So before we show what we ended up with after we merged all 8 of the different captures, here is what the graphs for one of those individual captures looked like within the DVRescue view. Now, you'll see that there is one kind of blip where there was an error that went across both of the heads right there at the very beginning. On this graph, the positive values represent one of the heads and the negative values represent one of the other heads. And then pretty much all the rest of the errors you'll see are all in the positive side, and so those all, according to our hypothesis, probably should have come from a head clog and should be completely repairable by the DVRescue merge process, as you probably shouldn't have that exact same clog that caused those in all the same places. So here is the graph of the file that was created post-merging all 8 of the captures together, and imagine our surprise when you can see here that the only thing that did in fact disappear from that was that initial blip there that should have been caused by damage across both heads. And everything else is left behind that we had hypothesized should be completely taken care of by a merge, particularly with 8 separate transfers of the same material. So we were pretty confused about what was going on with our results here, and we decided to dive into it in a little bit more detail to get exactly to the bottom of why we were still left with all of these apparent head clogs. So at this point, we're looking at the straight up raw XML that is created by DVRescue around all the tapes that you process through it. And so here, there's a few things I want to call out to your attention. First of all, you'll see the XML lines that have dsec, n equals, and then a number. And you note there that starting at 0, they all go up and they're all even. So these indeed are all occurring, errors occurring across the same video head in this capture process. Now I want you to take a look at the little red box that I put around TC with the timecode, and just want you to make a note of what that timecode is, and then we'll show you another segment of the tape damage within the XML here that we discovered when we looked a little farther into this file. So I've switched here to a chunk of XML representing data farther down in the file, and as you can see, if you look at the red square around the timecode, we have in fact moved farther into that program, but other than the positionality metadata, nothing else has changed in terms of the error metadata. So this really stood out to us and really started to get us scratching our heads a minute here as to how we could not only have something that was apparently a head clog that should have been taken care of by this process of merging 8 separate files, but how are we getting this exact same pattern of errors at multiple locations across the tape? Now, at this point in the DVRescue project and our debugging here, we hadn't actually made the GUI that you could drop the file into to kind of get a closer look at the results there. So we didn't have the next step available that I'm going to show you right now that really clears this all up pretty quickly. But we ultimately were able to figure out what exactly was going on here, causing these weird anomalies within the metadata. So we were able to figure this out without using the current existing DVRescue GUI, but having access to this GUI now makes this even quicker to realize, and maybe some of you have realized this already, but if you drop it into the DVRescue GUI, you can see here, both of those segments have exactly the same errors because they represent exactly the same footage being reused in multiple places within the same tape. So the serendipitous thing about this particular program that we were using was that it wasn't raw camera footage. It was actually an edited program that had been taped on DV, edited on a computer, and then taped back to DV that we were capturing. And so you can see here that these 2 different segments both have different time codes, but they have exact same recording dates, exact same and recording times, and exactly the same error ratio, etc., because all that metadata, both for original recording time and all the different error concealment, was getting transmitted through the whole process after the engineer had taped this back to the tape that we then captured from. So this was, in a sense, an example of a transfer where we weren't debugging our own transfer, we were debugging a transfer that had happened in the past. And fortunately, this was an example where none of the things that we had worried that this had kind of refuted some of our assumptions about how the merge process should work weren't actually issues here. The head clog wasn't a result of a clog on our tape. It was one that had happened at the original point where the original technician transferred the raw footage to their editing platform and then got transferred back onto that tape. And so we'd been searching for this original, this perfect file output from our capture, and didn't think that we'd gotten it, but we did realize that no, we had gotten the perfect file that was, in a sense, perfect in its imperfection, which is getting a little bit philosophical maybe, but it was a happy realization. And also, we were just happy that the persistence of this provenance metadata going through the whole chain from creation through our capture kind of showed another example of the benefits of capturing DV via FireWire versus other methods that people use sometimes to capture DV. And to close here, I just wanted to show an example of what that error concealment that's going on in those frames actually looks like, just to, again, highlight how awesome some of the tools available in DVRescue can be to help you with your debugging of any kind of quality issues that you have in your transfers. The whole errors that were behind all of the investigation that we just did, if you look on the left, those are not very visible just by looking at the frame, because the error concealment is doing such a good job there. But if you look to the right, you can clearly see with DVRescue's tools have changed the error concealment to the color of yellow, where that head clog is actually happening. Thank you for listening to this segment on debugging here, and I hope that some of these things can show you how DVRescue can be applicable to some of your own workflows.
Here is the latest version of the DVRescue Graphic User Interface, or GUI. DVRescue is currently available as a set of command line tools, and we are working to convert these into a single downloadable application. The software will be compatible on Mac, Linux, and Windows operating systems. Eventually, the GUI will contain all of the same functions as the command line tools, including dvCapture or transfer, dvPlay and dvGraph or analysis, dvPackager, dvMerge, dvGuidance or help, as well as debugging and settings menus. Currently, the analysis tool is operating in the GUI. You can import files transferred from DV tapes into the program for quality control review. Simply click the Add Files button and you can select as many files as you need to check for artifacts or issues. Once imported, you can review each file one at a time, along with all of the error metadata collected by DVRescue and generated for visual analysis in the graph and table views. For those of you who use DV Analyzer, this is a vastly improved replacement. Icons and color coding highlight different types of errors or markers in the file in order to intuitively assist the user in determining the cause, if a solution exists, or if the tape would benefit from a second transfer. As the video plays back, the cursor moves along the plot of the graph and down the table to corresponding rows. You can also jump to a specific place in either the playback viewer, graph, or table, and all three will move in unison to the same position. Download DVRescue and try it out for yourself. To learn more about DVRescue, you can check out related resources online. From the main MIPoPS page, you can access our blog, codebase, and all the latest documentation. For feedback, we highly encourage you to create an issue in our GitHub Issues Tracker. The tracker provides a transparent, community-based approach to meeting the needs of all users. Others can weigh in to brainstorm or concur, allowing us to prioritize development and ensure documentation is effective. This should also be your first stop when performing your own troubleshooting for DVRescue tools. If you're experiencing a problem, chances are someone else is as well, so you can see if any of the issues posted sound similar to the one you are encountering, and if there are any steps you can take to solve it. From the main DVRescue GitHub page, you can find the link to our daily builds. It's in the far right corner under About. Here you can download the latest version and keep track of our progress as we address development work, improve the GUI, help fix the bugs, and add the features that you ask for in the Issues Tracker. If you're uncomfortable using GitHub, just email us. We also have a documentation page where you can access additional resources. We'll be adding to this as documentation is finalized and new discoveries are made. This project is intending to provide context to not just how DVRescue, the software application, works, but as a holistic approach to comprehensively managing your DV collections, with everything from initial assessment to understanding format specifics, to how to set up a transfer station, to how to prepare tapes for capture. We aim to provide all the tools you need to manage and care for these physical objects. After using DVRescue, these resources will provide guidance for file care, identifying artifacts and potential resolution, as well as additional resources to help you digitally preserve the important content from DV videotapes in your archive.